recording. So yes, today we are going to be doing a final exam review, somewhat similar to Wednesday's class, except for this one's kind of a free-form exam review, so you guys can ask really any questions that you would like to go over, and we'll go over them. Typically what I tell my students for the exam one and kind of any of the in-class reviews is that when you ask a question, right, you should try to ask your favorite question. We are going to try to take turns and whatnot, and so we're going to try our best to make sure that to call as many people as possible. It'd be unfair if I just kept on calling on the same person over and over again. So yeah, make sure you ask your favorite question, and usually I find there's quite a bit of overlap and everything like this. Alec's going to be kind of choosing which questions we go over and the order and all that sort of stuff, but he's going to be following these same principles of trying to select different people to ask questions. And of course, if you type in your questions in the Q&A, that's certainly fine. I've downloaded some of the practice exams. I have both of the practice finals. I have some of the old exam ones and exam twos. I can go over any of that. I have on my desktop here, I've opened up the D2L scans of the textbook. And so I have kind of those ready to go. I have web work here in the background ready to go. And so I have a variety of things. If you tell me what the number is and stuff like this for the problem, I'm happy to look that up. And then we can also, if you'd like, you can use the raise your hand feature, and we can actually, enable your microphone if you'd like, right? If it's too much of a pain to write down what your question is, that would be another way to just verbalize your question. So that's what we're going to be going over today. I also see here, do you have a final exam question breakdown similar to what we had for exam two? So yeah, it'll be quite similar to exam two, of course, just a little bit longer, right? Because instead of 90 minutes, it's supposed to be 2 hours. But there is going to be some multiple choice, some true false, and some of kind of the standard web work style questions. And it's about at the same percentages, again, just kind of, a few more questions, because again, you get 2 hours and it covers the entire semester. So I don't have the exact numbers or the exact points down in front of me, but if I get a hold of that, I can get it, I'll post it on D2L. And in fact, I want to expand anyway this, right now it just says coming up next, study for the final exam. I'd like to expand that anyway. So if I get a hold of that, I'll go ahead and post that there. The last reminder, right, post-course survey due today by 5 p.m. Make sure if you haven't taken that, again, it's worth some extra credit and whatnot. Okay, I think that's all of my administrative announcements. I guess, always a good idea to get the final exam information on the video one more time. So again, our final exam is next week, Tuesday, April 28th. You have it's a 2-hour exam, and you have a bit of a window, right, from 9 a.m. until 4 p.m. Make sure you put that in your calendar. Of course, it's very unlucky to miss the final exam, right? The MSU has kind of strict policies as far as what's an acceptable excuse and things like this. And because it does end at 4 p.m., right, you want to start by 2 p.m. And all of these are the Eastern Standard Time. Okay, I think that's all of my administrative stuff. Anything you'd like to add, Alec?
Nope, not at this time.
Okay. So again, if you have math questions, please go ahead and start typing them out in the Q&A in the chat, and we'll go over whatever you're interested in. So Alec, what should we hit first?
Let's see. Well, there's a question here. Somebody's asking about stable internet on campus. Do you know anything about that? I am not sure.
I would suspect it. If you wanted to take, you wanted to go to campus to take the exam. I know places like Wells Hall and stuff like this are still open and unlocked and everything. So you could go take the exam there. I'm assuming some of the dorms are still open. Of course, I don't know any great ones with excellent study rooms and things like this. So I'd probably suspect one of the academic buildings. But yeah, I know the internet was still going strong last time I was there. So
okay,
that would be reasonable.
All right, now I just noticed something here. We're going to try and rotate around who's asking questions, and yet so far they've all come up as anonymous attendee. So,
well, we'll do our best.
okay. So I guess for starters, there's the first one in was, can we do examples 4 and 10 from the review problems? Why don't you go ahead, anonymous attendee, and just tell us which would you prefer, 4 or 10? We're going to kind of go with your favorite question first. So why don't you just jump in there right now and just say 4 or 10, and then we'll take that one first, whichever is your favorite. So this will be from the review problem packet.
Okay.
Okay, start with number 4 then.
All right. So, I mean, as promised, I did go ahead and fill out the rest of the problems that we didn't get a chance to go over in class. And so it's already filled in, but I'm happy to talk through it and kind of elaborate on the solutions. And then, of course, if there are any kind of specifics or things that you'd like to talk about in this problem, I'm happy to hit that specifically. So yes, we're interested in finding the volume of a solid generated by rotating the region in the XY plane in the first quadrant between a couple of curves here, right? We have the square root, y equals square root of x, and y equals 2 about the y-axis. So you can kind of see what the picture looks like here. And kind of it started off, I had just a 2D picture in both the XY plane. I drew the square root of x, so something like this, and I drew the line y equals 2, so something like that. Remember, it only says, in the first quadrant. So kind of, even though this line, does continue over here in the second quadrant, really we're just interested in the first quadrant. And so now I need to figure out, right, there's a couple of different regions, right? I see there's kind of a region up here, there's a region over here, there's a region over here, there's a region over here, right? Which region is it talking about? And again, it's in the first quadrant, and it's between these two curves, right? And it also mentions, this y-axis. So the only one that's between the two curves and the y-axis is this one right here. So this is the region that it's talking about. And we want to take this and we want to rotate it about this y-axis and figure out maybe what the volume of the solid is. And so that's where I get this picture here. I've taken it and I've rotated it about the y-axis in order to get this picture. And so on our formula sheet, the only kind of equation that we have for volume is that volume is supposed to be the integral of area. And so that we know we want to integrate area, and we can see from this, and this is where the picture really comes in useful, that we just need to use the disk method, right? That these are full circles, there's no holes in the middle, right? But the picture is where you tell, do I need to use the disk method or do I need to use the washer method? So in this case, because this region butts right up against the y-axis, the axis that you're actually rotating it around, when you do that rotating around, there's no hole in the middle. In comparison, if I was to rotate about, like x equals -1 over here, so the nice vertical line x equals -1, notice now this region doesn't butt right up against the axis that we're rotating around. And so when you rotate it around it, there's going to be this hole in the middle. And then you're going to need to use the washer method. So you would get something like this. So that's just kind of a refresher of when do you need to use the disk method, when do you need to use the washer method. Okay, the other thing is that I've told my students, there's kind of a nice rule of thumb here, that if you write the axis that you're rotating around in its equation form, so notice that this is, it just says the y-axis. If I was to write an equation for the y-axis, the equation for the y-axis is the x equals 0, And so we're trying to rotate it about x equals 0. And one of the questions that we need to ask, and on our formula sheet, by the way, it says that volume is just the integral of area, and I think it uses the variable x. But of course, we know one of the upgrades that we can do is that we could integrate with respect to y. And we have to know, when should we integrate with respect to x versus when do we need to integrate with respect to y. And so if you have the axis that you're rotating around in its equation form, so in this case, x equals 0, you're just going to do the opposite of this. So instead of x, we're going to integrate with respect to y. And this just deals with the fact that, x equals 0, perpendicular to that are going to be these different y levels, And those are the things that are kind of staying stable as you rotate around. And so, okay, that's kind of why this works out and why this rule of thumb is good. So we're going to integrate this with respect to y. Since we know now that we're integrating with respect to y, right, one of the things that we could answer is, what is the smallest y value in this region, and what is the largest y value in this region? And so again, because we know that we're in the first quadrant, we know that the smallest y value in the first quadrant is y equals 0, and we can say our region contains that point there. And then the largest y value, we'll notice that it gets cut off at y equals 2. So y equals 2, that's what's bounding this region in the xy plane here. And so the largest y value is going to be y equals 2. So that's where you get these bounds here from 0 to 2. And now we have to transform, right? We have a variable r, and I need to somehow transform this into some number of y's, right? I have to figure out the exchange rate between what is this r and how many y's is my r worth, right? Because luckily, we're still in single variable calculus. Right? There is multivariable calculus, that's math 234. Those days are coming, but right now we need to get everything in terms of just one variable. And so that's why we need to exchange this in. As you can see here, I've kind of spoiled it already, that r is going to be the same thing as y squared. Well, let's see where this comes from. We go back here, and looking at this, right, again, we go back to the picture, it's very useful to picture. The radius, kind of for each one of these disks, seems to be how much we're moving left and right. So we go to the picture and we see the radius for this disk is how far do I travel from x equals 0, the y-axis, x equals 0, in order for me to hit this curve. And this curve that I always seem to be hitting is this one right here. It's part of the square root, right? Y equals the square root of x. And the question is, well, how much do I move to the right in order to actually hit this? Well, moving left and right, that's the x value, right? How far do you move left and right is the x value. And so you may want to go ahead and solve this for x equals, right? And that length, that amount that you move to the right, that quite literally is the radius. When you look at this picture here, right, how much we move from x equals 0 over to this curve, that is the radius that makes this circle. So again, kind of you have to use the picture in order to figure out, you know, should it be the y value as the radius or should it be the x value as the radius? Sometimes you have to do extra things to this, but in this case, right, it's just the x value. How much do you move to the right from the y-axis? And so, okay, r is going to be the same thing as the y squared. So we go ahead and we plug this in. So instead of r, I get y squared. Of course, when you take powers and you raise them to more powers, they multiply. So that's why I get y to the 4th. Then we can go ahead and integrate and plug in 0, and we get our final answer, 32 pi over 5. Questions on this one here? Or things that you'd like to add, Alec?
There's one question that just came in. It says, if I was rotating around x equals -1, as you were sort of pointing out, for example, how would I set up the radius? So let's go back to that picture. That would make your radius larger.
Yeah, so we would need to know how much are you moving off of the y-axis still. So this x value right here, right? How much do you move left and right in order to hit this curve, the square root? But then you also need to, right, since you're rotating around x equals -1, right, you also need to move this extra 1 right here. So in this case, it's going to be 1 plus x. Again, we know the x value for this. It's still going to come from the same equation, y equals root x. And you could solve x equals y squared. And so 1 plus y squared, right, that would be the radius. But now this would just be the outer radius, right? You would also have to talk about the inner radius as well. Kind of a nice formula, and we've seen this multiple times for regions and things like this, right? Kind of if you take the outer curve and subtract away the inner curve here, this could give you this value. So kind of the outer thing, right, would be this value x, right? And then you need to subtract away -1, x equals -1 in this case. And so that's where another way to see kind of more of an algebraic viewpoint, right? I like this way where you can kind of visualize and see what's going on and everything. But if you like an algebra rule to memorize, right? X minus the -1, that's going to give you the x plus 1 here. And then, right, because we're integrating with respect to y, we would need to go ahead and transform this into y's. And so we use this exchange rate here.
And so that 1 plus y squared, then that's what would call the outer radius. A lot of times in class, I would use big R for that, a capital R.
Yep.
And then your inner radius would just be that smaller circle there, which just has a radius of 1.
Yes, so you would have something like this, minus pi and 1 squared. So in this case, our inner radius, like you mentioned, would be 1.
There's the whole setup.
Yep, and again, kind of you can just visualize and see, hey, your inner radius is just how far do you move here to here, right? Or you could say that this is x equals 0, and here we have x equals -1, and so you could quite literally take 0 minus -1, and that gives you your inner radius. So that, again, there's an algebraic way to view these things, and also kind of a graphical way to view these things. Okay, excellent. Where should we go next?
It's just so we're not skipping around like crazy. Let's do one more from right here, number 8 from the review problems. Then we'll switch to the 2014 final exam for a couple.
Okay, number 8. Yes, I was kind of actually surprised that this one didn't get asked in Wednesday's class, or didn't get upvoted as much. And so, yeah, for this one, we want to use the Taylor series generated, find the Taylor series generated by the function 1 over x at the point x equals 3. And kind of what I was thinking about here is that, remember, we have this nice list of lots of different formulas. They're Maclaurin series formulas. So there's a bunch of well-known power series. So things like sine of x equals all of this sort of stuff. We also have this one here, 1 over 1 minus x, and that's kind of a bit closer to what we want here. But remember, these are Maclaurin series. They're all centered about x equals 0. And so sadly for this problem, we can't use those because we want to have it centered around x equals 3. So sadly, we have to actually develop this formula from scratch. So there's no way to really use this. Even if kind of, you're clever and you try to do like a U substitution, you're not going to be centered around the right point, unfortunately. And so this is a case where, sadly, we have to go back to the original definition. So that's this bit here. So the original definition for the Taylor series is that you need to take a bunch of derivatives, right? We need the nth derivative of our function, and we need to evaluate it at that center. So in this case, 3. You divide it by n factorial, and you divide by x minus the center, a, and you raise it to a variety of powers. So in this case, I went ahead and I plugged in, right, we wanted to evaluate this around x equals 3 to be our center. So I went ahead and everywhere I saw an a, I plugged in a bunch of 3's. Then we have to figure out, right, a lot of this is well known, but the only thing that we still need to figure out, it's still a bit unclear, is how can we figure out a formula for this nth derivative of our function at 3. And so this is kind of a pattern finding exercise where you need to do a couple of these things, kind of see what the pattern is, and then try to state what the pattern is in general. And so I go over here, I take 0 derivatives, so it's just 1 over x, I plug in 3. Sorry, let me go ahead over here. Then I can take a derivative, so I take the derivative, notice the -1 comes down, we reduce our power by 1, and then I plug in 3. So that gives me this answer right here. I get 1 over 3 squared. Next up, I take yet another derivative. Now the -2 comes down, right? And I reduce my power, and it becomes x raised to the -3rd power. So now I can plug in 3 to that, and I get this answer over here. So notice I have 1 times 2, and then I'm dividing by 3 cubed. And my suggestion that I've mentioned in class several times, and it's good to mention it again here, is when you're doing these sorts of problems, I would recommend not simplifying. Even if things could cancel, which right now they really can't, but even if things could cancel, you should resist the urge to cancel them, because sometimes when you cancel these things, it kind of hides the pattern. So notice in this last one right here, even though I could cancel a 3 on top and a 3 on bottom, I suggest that it's a good idea not to do this. Don't cancel these things, because then you're kind of hiding the pattern. Notice, okay, then we're going to have divided by 3 to the 4th power. And so I kind of see a sort of deal, some pattern going on here. I notice that this right here, this 1 is the same thing as 0 factorial, for instance. This one, you could imagine that's the same thing as 1 factorial. 2 times 1, that's going to be the same thing as 2 factorial. 1 times 2 times 3, that's going to be the same thing as 3 factorial. And remember, we're trying to come up with a formula that's based on the number of derivatives that we're taking. Remember, I want to come up with a formula. If I take n derivatives, what should I get, right? And sorry, I forgot, I kind of canceled things over here, but notice that this one right here is negative. This one right here is positive. You have 2 negatives being multiplied. This one right here is negative. We have 3 negatives being multiplied together. And so we can see that however many derivatives you're taking, we have this n factorial, right? So when I take 3 derivatives, I have 3 times 2 times 1. So there's that 3 factorial. It seems to be alternating. So I have this minus plus sort of deal. So -1 to the n. And then notice that when I took 3 derivatives, I had 3 to the 4th power in the denominator. When I took 2 derivatives, I had 3 cubed. Right? It always seems to be 1 more than the number of derivatives that I'm taking. So if I take n derivatives, it looks like there's 1 more 3 on bottom than the number of derivatives that I took. So I think this right here is a good formula for the nth derivative for my function evaluated at 3. So again, you do a couple of these things and you try to figure out what the pattern is. So remember, we've tried to figure out patterns before back in 11.1. 11.2, and of course now we're using these skills quite significantly here in these sort of 11.10 style problems. Now that I have a rule, I can go ahead and I can plug this in, just like I have here. So the nth derivative, and notice there's quite a bit of canceling that happens, right? Because there was an n factorial on top, but there's also this n factorial on bottom. So these right here can just cancel. The alternating piece remains, and the fact that we're dividing by 3 to the n plus 1 remains. So this right here is my final answer as far as what should the Taylor polynomial for this function centered around x equals 3, what should this look like? And then for part B, once we have a series, remember we can always ask, and this is 11.8 style question, what is the radius or the interval of convergence for a power series? And the answer 100% of the time for these is always the ratio test. We can use the ratio test, so that's what I'm doing right here, applying the ratio test to my particular series. You can see that there's going to be a lot of things that cancel out. You can apply those absolute values and everything, and it turns out that again, our center is 3, and our radius of convergence is 3. And if you go ahead and split up this absolute value inequality and kind of rearrange things, well, if your center is at 3 and your radius is 3, so you can take 3 steps to the right and you can take 3 steps to the left, right? Then you're going to have the interval from 0 to 6. So again, kind of there's an algebraic way, there's some algebra rules that say, hey, you can do this with absolute value inequalities, but there's also kind of a graphical viewpoint, right? If your center is 3 and your radius is 3, then we know, well, you can take 3 steps to the right, 3 steps to the left off of the center, and that's where we get 0 to 6. Now, one last thing before I kind of open it up to more questions about this. Notice that this did say the open interval of convergence. With the open interval, you don't care about the endpoints. But we've also seen scenarios, right, where it just asks for the full interval of convergence, right? And it doesn't specify this term open, right? In which case you want to know at those endpoints, right? Should 0 be included here? Should 6 be included here, right? And for those, we need to actually plug these in to our original series and test those. So we'd plug in, for instance, 6, or we'd plug in 0 into this, and we would need to test those in order to see what's going on at those values. Okay, good. Things I'm missing, questions on this, things you'd like to add, Alec?
There's just one question that came in and said, is there double jeopardy with stuff like this? For example, if you get A wrong, does it immediately lead to getting B wrong? Well, in the when we had free response questions like this, like on this exam, what we would have done is very carefully, if you had gotten A wrong, we would have taken your answer from A, as long as it was of sort of an equal difficulty level, and we would have followed it through and seen if your answer for B was consistent, and so you wouldn't have lost any additional points. Now that it's done on WebWork, it's done a little differently. Sometimes these things are split up into maybe two separate problems to kind of avoid that issue. In other cases, you might not kind of open the second part till the first part's right. I don't know, maybe you could address that a teeny bit more, Ryan?
Yeah, so definitely I agree with everything that you've said, especially, you know, the fact that it needs to be of equal difficulty level, right? I mean, if you kind of got an answer that's, you know, very simple, you know, just 1 to the n or something like this from n equals 0 to infinity, it's very possible that you're getting some points marked off for B just because you've significantly altered the problem. And so you were not seeing really the same skills being tested when you solve this one that you had to showcase when you're solving with the correct answer. With WebWork, some of this is also, and I agree with Alec, that we're much more likely to separate these things into multiple pieces and multiple problems rather than just kind of having these multi-step problems. And when we do have kind of these multi-step problems, I mean, to some extent, we're relying on the fact that you get 2 grading submissions when you're doing this. So that way, if you get something wrong, right, the multiple grading submissions is kind of another attempt at partial credit with these sorts of things. And so that's also a possibility that we could have multi-step problems, and just kind of the fact that you get 2 grading submissions, right? You don't normally get that on a regular in-class exam.
All right, so I think we're ready now to move on to, we've got 1 WebWork and then 2 2014. So why don't we move to the 2014 final exam and start with question number 5.
Question number 5. Consider the function defined by this thing here, this power series. It looks like not exactly a power series, but a fancy series anyway. Evaluate f of x in a simple formula with no summations, assuming that the series converges. So this one is nice. It's kind of, it reminds me of our 11.2 days to some extent, right? So we remember there was a nice formula in 11.2 days that said if you're summing up a times r to the n, and n is going from 0 to infinity, that this converges, and we know what it converges to. So in this case, it's going to converge to a over, put the a somewhere, a over 1 minus r, right? And so this was the geometric series test. And this is true when it converges, and the condition is that the absolute value of r should be less than 1. So in this case, notice that r is now sine of x, right? The thing that's being raised to a variety of powers of n is sine of x. And then our a, if you really wanted to do an a, right, you could just put a 1 out here. So in this case, we can rewrite it sum from n equals 0 to infinity of 1 times sine of x raised to a bunch of powers. And so this is going to be equal to 1 over 1 minus and sine of x. And double check, right, whenever right, you're saying what it converges to, this lower limit of the summation really matters, right? For many of our tests, we're only trying to say, does it converge or diverge, right? We're just basically trying to distinguish between infinity versus a finite answer, right? And so quite often it doesn't matter what you're actually starting with. You can start at n equals 1 or n equals 2 or n equals 5, and that's not going to really change between the answers infinity or not. However, if you want to say it converges to a specific value, like with this geometric series test, the lower limit, this lower bound for our summation really does matter. And so the fact that this starts at 0 and the geometric series test, you know, condition is that you need to start at 0, then we can go ahead and apply it. So our final answer here would be this is 1 over 1 minus sine of x. And then part B to this, for which values does the series converge? So remember, we need to have the absolute value of r less than 1. And so, well, in this case, our r is sine of x. and we want the absolute value of this to be less than 1. And so, well, sine, remember, this kind of ranges between -1 and 1 anyway. Something like this, it goes negative as well. And so this is going to converge darn near everywhere. The only bad points is when you took the absolute value and you would be equal to 1. So something like here, something like here, something like here, here, here. And so we need to go back to our trig days for a little bit, and basically anything but an odd multiple of pi over 2. So it's going to converge darn near everywhere whenever x is not equal to, and if you wanted the shorthand for this, right, it would be kind of k, well, let's see, I was going to do k times pi over 2, right? But that's not just an odd multiple of 2, this is any multiple of pi over 2, right? And so we need to take special care to make sure it's odd. And right, the easiest way to write down an odd number is just to make it 2k plus 1, right? So something like this. So an odd multiple, right? Because if we just had, 2 pi over 2, that'd be pi, right? That'd be down here, right? That's going to converge, right? So you're not going to have sine is equal to 1 there, or -1, and so it would converge. So you have to make sure that it's odd. So I think this is maybe how, it's been a while since 2014. I don't remember how exactly they wrote down the answers for this, but you could also just list them, right? So x is not equal to, you could say -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2, and just list a couple of them, see the pattern sort of deal, and then do the ... right? To say that, hey, this pattern here, this continues. So it's going to converge everywhere, but when sine is 1 or sine is -1. Questions, comments, things about this problem? Okay.
Looks like we're good there. Let's move on to problem 13 from that same exam.
Problem 13. Consider the curve in polar coordinates. Theta is ranging from -pi over 2 to pi over 2. Give an equation for the curve in Cartesian coordinates. So in Cartesian coordinates, well, remember we learned how to exchange from polar coordinates to Cartesian coordinates, right? And there's a handful of these nice formulas that help us exchange one for the other. And again, these are on the formula sheet, so I definitely recommend that you have the formula sheet printed next to you, sort of deal when you're taking the final exam. They go like this, right? So we have x is equal to r cosine theta. We have y is equal to r sine theta. And we have x squared plus y squared is equal to r squared. So this gives us kind of what we can exchange. In this case, we're given r equals 2 secant theta. And we'd like to exchange this for some number of x's and y's. And so let's go ahead and take a look at this, right? R equals 2 secant of theta. The problem is, right, I don't see any secants over here. So that's maybe my first thing that I'm running into. But remember, secant, we can actually build secant out of sines and cosines and things like this. Remember, it's just the reciprocal of cosine. So secant is just going to be 1 over cosine of theta. So we could rewrite it like this. And from here, there's a couple of different ways that you could go. All the paths, end at the same correct answer here, so long as you don't mathematically, alter anything. But one way that you could go about it is that, you could say, well, none of these have cosines on the bottom. So we could bring cosine up into the numerator. And maybe my favorite way to do this is just by multiplying by cosine on both sides. And so I'm going to get r cosine of theta, bringing that to the other side, is equal to 2. And now we can see, well, that's exactly what x is. So we get x is equal to 2. And this is a perfectly good equation in Cartesian coordinates, right? We know what this looks like. It would just look like x equals 2, a nice vertical line here at the x value of 2. And remember, sometimes the Cartesian coordinates, Cartesian curves, even though they're allowed to have x's and y's in them, not every single curve, has both an x and a y, right? There are plenty like this one here that just has x's, or you've certainly seen things like, y equals 3, right? Which is just a nice horizontal line at height 3. So this would be another perfectly fine Cartesian equation. It just doesn't happen to have any x's in it, right? And so even though it's allowed to have x's and y's, it doesn't need to have both x's and y's. So in this case, the fact that it only has x's shouldn't be that alarming. So that's 13a, and then 13b, set up an integral in polar coordinates representing the area of the region bounded by this curve in the lines theta equals 0 and theta equals pi over 4. Do not evaluate. So, okay, we could go ahead. Theta equals 0 looks like this line right here. So that's what theta equals 0 is. Remember, you could have positive radiuses or negative radiuses. And then theta equals pi over 4. Remember, no restrictions on r here, right? R could be 1, r could be 2, r could be 3, right? So it looks anything like this. Could also go backwards. Something like this. And we want the area of the region bounded by this curve and these two lines. So the only curve, or the only region that touches all three of these things, and it's bounded by these three things, is this region right here, this triangle. And so we want to set up an integral in polar coordinates. Well, in polar coordinates, right, the area formula that we get goes something like, it's going to be the integral from alpha to beta of, and it goes 1/2 r squared d theta. So in this case, well, we need some theta values since we're integrating with respect to theta, and unsurprisingly, it's 0 to pi over 4, right? Those theta values that were given here come back. And then we have 1/2, and really we're only given one r equation, and that's just this one here. So that's going to be 2 secant of theta, quantity squared, d theta. So now we've set this up, right? It says do not evaluate, but actually integrating secant squared isn't all that bad. You could actually evaluate this. And because it's a triangle, right, kind of geometrically, we could check our answer as well. So this one wouldn't even be all that bad to actually evaluate. The other thing is that, so I kind of just did, almost did it by a process of elimination here. But I said, there's only one thing that we're calling r. We should just plug that in for r, right? There's also a geometric viewpoint that kind of says that we're doing the right thing here. So remember, as our theta values range from 0 to pi over 4, so kind of the smallest one is theta equals 0, the largest one, theta equals pi over 4, this direction, right? And kind of what we talked a lot about in 10.4 is that we ask ourselves, how do I enter into this region, right? What's my inner radius? And how do I exit this region? What's my outer radius? And notice as soon as you take the tiniest step off of the origin, you're already inside of the region. So as soon as you pass r equals 0, you're now inside of the region. And the way that you exit this region is through this straight up and down line here, right? And that straight up and down line, well, that is the r equals 2 secant theta. So that should be our outer radius, this r equals 2 secant of theta. And so kind of the full equation, even though, and we have to know that there's right, an expansion for this, right? And it goes that you should be integrating from alpha to beta, 1/2 the outer radius squared minus 1/2 the inner radius squared. And it's just because this region actually comes up and butts right up against the origin there, right, that this inner radius is just 0. And so you get the exact same result, but this may be another way to view this problem here. And just kind of make sure that you're doing things correctly. So this may be another way that people are thinking about this style of question. Good. Questions about this problem here before we move on?
There's one question here. It just says, is it coincidence that if you evaluate it, you get 2 tangent theta, which is what y would equal if you multiplied by sine in part A?
This is a question that if you evaluate, you get 2 tangent of theta. So if you were to actually evaluate this, you do get 2 tangent theta. I agree with that, which is what y would equal if you multiplied by sine in part A, which is what y would equal if you multiplied by sine in part A. Yes, that's very much a coincidence. I don't know of any rule or any way to be able to expand this to a general case or a general problem. So yes, I think this is probably just coming from the fact that this one happens to be a triangle. And remember, there's a lot of nice relationships with triangles and trig functions, unsurprisingly. But kind of if you have something a little bit more horrible than a triangle, let's say, you have something where you have, a circle cut out, and then maybe like a wedge like this or something like this. I'd be very surprised if there was any sort of relationship between kind of the y value and what the integral for this would be equal to.
There might be a little clarification. I'm not sure if this is the same person. Again, it's just coming up as anonymous attendee, but somebody said 2 secant theta times sine. Well, if you go back to where you see, r is, x is r cosine theta, right? Y is r sine theta. So if you know what r is there, then yeah, if your y value would be r times sine of theta, right? So if that's what you're asking, yeah.
Oh, I see.
Yeah, I don't think so. Maybe that was a clarifying question right there. So
okay,
that makes sense then. Let's see. I think we did 12B from the 2014. That's the one you just did, right?
No, this was 13.
Oh, that was third. Okay.
But actually, so 12B here, this one got asked on Piazza as well. And this is kind of an old style of question. Really, we've never really talked about the parametric formula for a tangent line. And so this one really wouldn't be so appropriate to ask like this, here in 2020. So this is back when they had a different book. I think they were using Thomas calculus and whatnot. Instead of doing a Cartesian equation for the tangent line, sometimes they did a parametric formula for the tangent line. And so I would say that you don't need to know this. Again, there were no learning set problems, there were no assessment set problems or anything like this for parametric formulas of tangent lines. So it's okay to skip this one.
Yep. Okay, there had been a question up. I don't know if I accidentally dismissed it or something. No, I didn't dismiss it. There had been a question up about a WebWork problem. And I don't know if was it taken down? I think maybe it was taken. Oh no, there it is. Oh, it was answered live. I think I clicked the wrong thing. Okay, this person's been waiting a long time. WebWork 10.4, number 13.
WebWork 10.4, number 13.
Yeah, I accidentally clicked answered and it wasn't. So let's do that
one. All right. WebWork, I'm assuming 10.4, and you said number 13.
Right.
Find the length L of the curve given by, the curve given in polar coordinates by the equation R equals e to the 3 theta from theta equals 0 to theta equals 2 pi. Yeah, so let me go ahead. I think we did one quite similar to this in class. So let me maybe pull this up. And maybe the only thing that we didn't have was this 3. So we'll just see kind of how that 3 would alter things. So let's go back really quick. For the in-class filled notes, this would be chapter 10 stuff that we did in class. And I think this is the first day of 10.4. Remember, I kind of did things a bit out of order. So I had one day dedicated to less nice areas. And then I had one day that was dedicated to polar arc length and nice-ish areas, right? So not yet kind of full strength. And so problem 14, we started off by doing a relatively nice curve and we calculated out the arc length there. And then in example 15, we did one that's very, very similar, right? And like I said, the only difference is that in WebWork, it has a 3, right? And so why don't we go ahead and see how this would alter things, and we'll just kind of sprinkle in some 3s wherever we need them, sort of deal. And so remember, for the polar arc length, you need to take the radius and square it. So in this case, we'd have r squared, and then you need to take the derivative of r and square that. So the derivative of e to the 3 theta, right, there's going to be this extra 3, because when you take the derivative, you have to apply this chain rule. And so when you square this, right, and you can see that kind of I just left these things kind of separate, so this would still have 3. So here you have 1, and then here you're going to have 3, and you need to square that, right? So when you square 3, you're going to get 9. So notice this 2 is actually going to be a 10. But otherwise, right, so this 2 is going to be a 10 here. Here, when you take the square root of something squared, right, they just cancel, so you're going to be left with that 3 there. Here we're going to have still a 10. Here we're going to have a 3. And then when you integrate this, this should be 10. This should be 3, right? So you need to use the chain rule in reverse, or this is kind of a small u substitution. So you would get a 3 in the denominator. Double check. If you take the derivative of this, you should get back to where you started, right? That 3 theta, when you take the derivative of that, you would get that extra 3 there. And so again, this is kind of, it's quite similar to one that we did in class, except for you need to just kind of see what does this extra bit, this 3, how does this influence your answer? But so long as you're careful and you, right, notice that we had to square a 3 there and all that sort of stuff, that it is still quite similar. But the big thing here, and this is again on our formula sheet, kind of what we started with, whenever you want arc length for polar form, right, and we have 3 different arc length equations, right, it goes the square root, all of them have a big old square root, it goes r squared plus the derivative of r with respect to theta, quantity squared, add those together, put them inside of the square root, and integrate that with respect to theta. Of course, right, if you had a different style equation, right, so if you had a Cartesian equation, something with x's and y's, you would use the Cartesian form for arc length. And if you had something with t's, something that was parametrized, you would use the parametrized form of arc length. And so it's just basically however the problem's given to you, right? If the problem's given to you with r's and thetas, use the polar form. If it's given to you with x's and y's, use the Cartesian form. And if it's given to you as a parametrized set of equations, something with t's most likely, use the parametric form for arc length. So, yeah. I guess anything you would like to add, Alec?
Nope, that covers it pretty well.
Okay. What should we do next? Or any follow-up questions on this before we move on? All right. So I guess what should we do next?
Okay, so there's one that I asked a clarifying question, and so it's under answered. But the question was, it says on the second midterm, so this was the one on web work on page 8. Why does tangent of 1 over n summing from 1 to infinity converge by the nth term test? Isn't it possible that it doesn't converge despite this? So while Ryan's pulling that up, let me answer the first part of it first. Yeah, you can never show convergence by the nth term test. In fact, if you might want to use the full name, it's called the nth term test for divergence. So sometimes the nth term test is wonderful because if you take the limit as n approaches infinity and the terms themselves are not going to 0, then you're done right there. The thing diverges by the nth term test. In this case, though, as n goes to infinity, tangent of 1 over n will go to 0. So then the nth term test is actually inconclusive. So really, you need some other test to decide if that converges or not.
So yeah, I'm sorry if I go to the web work, because I didn't take the exam while it was open. Right, if I do, right, I don't have it in my previously generated versions of time sets. If I go and I try to take it, even as a instructor, exam 2, it gets mad at me. So I don't have the statement of the question. So could you repeat it for me one more time?
So I think I've answered the general question. It talks about the series, I guess, summing from 1 to infinity of tangent of 1 over n. And the question had to do with the person's asking about does this converge by the nth term test? No, in this case, again, the nth term test is inconclusive.
Yep. Exactly what you said. I would probably just reiterate everything, exactly as you said it. Nth term test can only be used for divergence. And so sadly, it does not have the capabilities to ever conclude that something converges.
Yep. And then let's see. We've got more questions than we can answer here. Final 2014. So back to that same exam on number 11B.
Okay. Okay, we have something here, converges or diverges because the blank test. The test applies because blank. Okay, so let me go ahead and rewrite this for a second. E, right, whenever we have something raised to a negative power, this is really secret division. So I want to rewrite it like this, just to kind of see what we're doing here. And so I'm just kind of thinking, down the list, kind of what we went over in 11.7 strategies for these series, right? How do we tell whether it converges or diverges? Right. The first thing that I would think about is maybe the ratio test, right? Does the ratio test work with this? And so I see an n, so I'm not particularly happy with that. But I do see an exponent, right? This e raised to some powers. And so I'm hoping that actually the ratio test would apply to this. So I'm going to try the ratio test. And so let's go ahead. And we're going to do the limit as n goes to infinity, the absolute value. And I need my a sub n plus 1s. So n plus 1 divided by e to the n plus 1 quantity squared. And then I'm going to go ahead and divide that by a sub n. And I'm just going to multiply by the reciprocal here. And so this is going to be e to the n quantity n squared divided by n inside of absolute values. Now, as n goes off to infinity, right, all of these things are positive. And so these absolute values really aren't so needed. So I'm going to drop the absolute values. And then the other thing that I like to do with the ratio test is that I like to combine all of the like pieces. So in this case, we have the n plus 1 and the n. Right, they kind of come from the same piece. And then I have these exponentials, this e to the n squared divided by e to the, and I'd like to FOIL all this out. I think it's going to help me maybe simplify a little bit. So if I FOIL out n plus 1 times n plus 1, we're going to get n squared plus 2n plus 1 once I have this all FOILed out. And so now let's think about these one at a time, because limits, right? For instance, derivatives have like a really nasty product rule. You have to do the derivative of the first times the second plus the first times the derivative of the second, all that sort of stuff. But limits, they had just a great product rule that you can just basically apply the limits to each piece. So I can think about what does the limit of this piece equal as n goes to infinity. And as n goes to infinity, right, we're going to have infinity over infinity. So I could apply L'Hopital's rule. And this is just going to be 1 over 1. So if you want to use L'Hopital's rule for this, it certainly works. This is also a polynomial divided by a polynomial. So you could also just use this kind of old algebra fact, right? That these polynomials have equal degree. They're both raised to the first power. And so the limit's going to be the ratio of the leading coefficients here. So 1 divided by 1 gives you the 1 there. Okay, so that's nice. What's a little bit more difficult, and so I'll take an extra line to do it here, is how does this kind of simplify down, right? If you plug in infinity in both the top and the bottom, you do get infinity over infinity. So you may be tempted to try to use L'Hopital's rule with this. And I think you'll end up just kind of spinning your wheels for a while, right? Because the derivative of exponentials, they always have, a copy of that exponential. And so things won't really simplify or cancel so nicely. But there is this nice property here for exponentials, right? Kind of if you have, and I'll write it in the general form here, if you have a to the b, and you divide it by a to the c, this is equal to a to the b minus c. That if you have these like bases, that the exponents subtract when you divide these exponents with the like bases. And so I'd like to do that here. So I'd like to go ahead and subtract, right? N squared minus n squared plus 2n plus 1. And so I'll go ahead and subtract these things. Well, 1 times anything is just that anything. So I'm going to drop this multiplication by 1. And when I go ahead and I subtract these, I get e to the, right, and there's a little bit of canceling out, but I still have to distribute this negative piece here. So negative 2n and minus 1. Or I could just leave this, right, as negative and the quantity 2n plus 1. My next step, right, I want to plug in infinity for n, right? I want to see what kind of happens with this. And again, just like I did at the very beginning, sometimes with these negative exponentials, I think it's actually hiding from us what's really going on. And so I'd recommend anytime you're trying to evaluate, when you have a negative exponential, I would kind of rewrite it in terms of division. And so this is going to be 1 over e to the 2n plus 1. I'm going to use up that negative exponential here and really write it for what I really view this as division, right? So usually I call negative exponents just secret division. And so, okay, as n goes to infinity, we're going to have here 1 over e to a very, very large number, 1 over e to an infinite power. So e to a million, e to a billion, right? When you take e and you raise it to a very, very large power, as you can imagine, it's going to be very, very large. And so when you take 1 and you divide it by an extremely large number, right, this is going to go to 0. So you're going to have 1 times 0. And that's why you just get 0 here. So after all this, we have to kind of think back to what were we doing at the beginning of all this? Oh, well, we were applying the ratio test, right? And so the ratio test is really an exploration when you take these, the limit of these subsequent terms, like the ratio of subsequent terms of our series here, right? The condition is this less than 0? Is it greater than 0? Is it equal, sorry, I kept on saying 0, I meant 1. Is it less than 1? Is it greater than 1? Or sadly, right, sometimes when it's equal to 1, it's inconclusive. So in this case, it's less than 1, so we know that it converges by the ratio test. So to answer the question here, it converges because of the ratio test. The test applies because, well, there's not a lot of hypotheses for the ratio test. I mean, we have positive terms, but you wouldn't even need positive terms. It's fine with alternating terms and everything like this. Computations to apply the test. Well, I'll just say that the limit as n approaches infinity of a sub n plus 1 divided by a sub n is equal to 0, which is less than 1. So, I mean, that's not exactly why the test, applies. Because again, the ratio test really doesn't have so many hypotheses here. You just need kind of some series. But it is what gave us the conclusion, right? Why it was convergent rather than divergent.
Yeah, you could probably say the test applies because the limit wasn't 1. That's really the only time that it doesn't apply.
Yeah.
You're able to do the limit and it wasn't 1. There was a follow-up on this one. Somebody asked, wouldn't it be easier to write e to the 2n in parentheses? And that's actually not the same thing. If you have e to the n in parentheses and then that whole thing is squared, then yeah, when you raise a power to a power, you can multiply, as Ryan's writing right there. That would be the same thing as e to the 2n, all right? But that is not the same thing as e to the n squared. So it would be nice, but unfortunately, no, you can't. You're stuck with e to the n squared.
Yeah, this is one of these things. They look very similar. And whenever you're wondering if something applies or not, I would recommend plugging in like a specific value or so. So for instance, if you just tried plugging in n equals 1 to see if these were the same, this one right here would give you e to the 1. Oh no, this is a bad, I guess I'd have to do n equals 3 would be a reason 1. So n equals 3. So you'd have e cubed, and you're raising that to the second power. So again, here where you have powers raised to more powers, they would multiply and give you e to the 6th power. In comparison, for this one, you'd have e cubed, and you have to take the 3 and you square it. So when you take 3 and you square it, you get 9. So this is e to the 9th. So this is one case where you could see that these are not equal. That really, versus is as good as you can say, right? These are actually different functions, and if you graph them, they look different. All right, well, I know, Alec, you had something special for us, right? To something that you usually do like for the last class, because I see we're getting pretty close to 3 o'clock here.
Yeah, we'll stick around and answer a couple more questions maybe afterward. But yeah, sure, for the, I'll turn my video on here. And if I can here. All right. Why do I not have the option to turn my camera back on? Oh, here we go. All right, there we are. All right, so yeah, for some of you who have been in my class, you may have heard rumors that sometimes I'll do a little song for people at the end, and something that that students somehow got wind of over the years. I didn't do it at first, and then people started asking, and they seem to like it. So I'm going to sing a little song for you, but first, I got to put on my blues hat. All right, just a silly song for the last day of calculus. I got a chicken. His name was Fred. I forgot to feed him, and now he's dead. Oh. I got those chicken blues. Ain't got no chicken, ain't got no life to lose. I got another chicken. His name was Sam. He got run over. Oh, damn. I got those chicken blues. Ain't got no chicken, ain't got no life to lose. I got one more chicken. His name was Chet. I remembered to feed him, and he wasn't dead yet. Chet got in a jam, couldn't save his hide. He met Colonel Sanders, and now he's deep fried. I got those chicken blues. Ain't got no chicken, ain't got no life to lose. That's been a pleasure, you guys.
I was actually watching the numbers here. I think we actually gained a person while you were doing that. I was wondering if there was going to be like a huge drop off or anything, but no, you retained everyone. I think you gained a person.
All right, just fun on the last day.
All right, so I'm going to go ahead and stop recording here. It's been a pleasure, guys. We'll go ahead and take a few more questions.